Hello, everybody. Welcome back to our continuation of cellular respiration processes. We are now going to talk about steps 2 and 3, which is acetyl-CoA formation and Krebs cycle. So at the end of glycolysis, we produced two pyruvic acids, right? We had two of these pyruvic acids. They're just showing one for simplicity's sake. So everything that happens here on this diagram will be happening double, one for each pyruvic acid produced in glycolysis. So there's multiple things happening in this step. They're showing two arrows, but there's really three enzymatically driven steps that are happening. The first one is what we call a decarboxylation. In this process, a carbon dioxide is removed. So they've kind of highlighted it in the purple right here, showing you one carbon and two oxygens in that pyruvic acid molecule is being removed as carbon dioxide. So that's part of the CO2, those 6 carbon dioxides that we are exhaling at the end of cellular respiration. 2 of those are being formed here in the acetyl-CoA step, 1 from each pyruvic acid. And then this little hydrogen that we see here is this same little hydrogen here that's just going to be now connected to that carbon. So this hydrogen comes over and forms a bond with that carbon. All right, so we have this molecule is now called acetate. We've just lost a carbon and 2 oxygens. The next step is kind of a 2-for-1 deal. So each one has got its own enzyme. So these little blue circles are representing the enzymes. I'll just go with step 2. That hydrogen that kind of scooched over and connected to the carbon when the CO2 is removed is now swapped out for this CoA. So you can see this guy goes away and the CoA comes into place. And so now we have what's called acetyl-CoA. Just swaps out that hydrogen. And with that hydrogen, right, because that hydrogen could carry some electrons, and that's exactly what it does. So here we have acetate, plus NAD plus goes to acetyl-CoA plus NADH. Hey, what's that? That's another redox reaction. So who's getting oxidized and who's getting reduced? Well, we know that we can see this little hydrogen here that probably has an electron hanging around it in that covalent bond between the hydrogen and the carbon. And so when we swap off that CoA and at the same time we're doing this redox reaction, that is going to be swapped onto that NADH with that electron coming with it. So this is our acetate is being oxidized, NAD plus is being reduced. Okay, very similar to what we saw in glycolysis with the G3P being oxidized, the NAD plus being reduced. Okay, so that's our formation of acetyl-CoA. So now we get 2 acetyl-CoAs produced per glucose, 1 acetyl-CoA per pyruvic acid. So now this is like a little bridge connector between glycolysis and Krebs cycle. So let's take a look at cycle. So here was our formation of acetyl-CoA. So that just came from step 2. And if you'll take a look, Krebs cycle is a cycle. It's this cyclical process driven by enzymes. Every single one of those little blue numbered circles is representing an enzymatically driven step. Again, you don't need to know the names of the enzymes or all of these intermediates. But again, the takeaway, what goes in, what goes out, and why. So the first step of Krebs cycle is to actually hook that 2-carbon acetyl-CoA group onto the last step of the prior spin with what's called an oxaloacetic acid. So oxaloacetic acid is a 4-carbon, that's this guy right here, a 4-carbon molecule plus the 2 carbons in acetyl-CoA gives us citric acid, which is a 6-carbon molecule. Sometimes Krebs is also called the citric acid cycle or the tricarboxylic acid cycle because there's 3 carboxylic acids in citric acid. I call it Krebs just because it's easier to say when you're teaching. These shortcuts I learned over the years. So the first step is hook those 2 carbons from the acetyl-CoA onto the last step of the prior spin to oxaloacetic acid, and the CoA just gets knocked off. It's just a temporary, it's a coenzyme. And we know, hopefully you might remember, coenzymes are there to help enzymatic reactions take place. So enzyme number one, we need that CoA to make the acetyl-CoA substrate fit properly into the active site. Okay, so now we have citric acid. And if we take a look at step 2, we don't lose anything, we don't gain anything, we just produce what's called an isocitric acid, just rearranging the atoms a little bit, maybe so it can fit into the next reaction, which is our step 3. And hey, look, there's an NAD plus and an NADH. There's probably going to be a redox reaction going on. So let's take a look. I'm just going to abbreviate here. Isocitric acid plus NAD plus goes to alpha ketogluteric acid plus NADH. Okay. Now we've kind of seen this pattern a couple times already. So where do we think the electrons are coming from? Who's getting oxidized? Who's getting reduced? Well, we see the NAD plus turns into NADH at the product. So we know there's going to be electrons probably hanging out with that hydrogen. So where did they come from? They had to have come from the isocitric acid. So this got oxidized, isocitric acid got oxidized, NAD plus gets reduced. And it changes their identity. So the isocitric acid gets oxidized into alpha ketogluteric acid, and NAD plus gets reduced into NADH. We're just shifting those electrons. And if you'll also notice, we get a carbon dioxide, so another decarboxylation reaction. This is just, again, the product of the CO2 that we're breathing off. Remember, we had 6 carbons that went in with glucose. We've lost 2 of them already with the acetyl-CoA decarboxylation, and now we've lost 1 more. So we've accounted for 3 of the 6 carbons that came in with the carbon in the glucose. All right, so here is our next step. We have our alpha ketogluteric acid, and hey, look, it looks like another redox reaction. Who do we have here? We have alpha ketogluteric acid plus NAD plus goes to succinyl-CoA and NADH. All right, so can you at this point predict or identify which molecule is getting oxidized and which molecule is getting reduced? Remember, look for your clues of the transferring of the hydrogen, who's gained the hydrogen, which means it's got the electrons with it. Right, that's the easy one to identify. That guy right there, the NADH. So if that's what gained the electrons, that means the electrons started with the alpha ketogluteric acid. So you are correct, hopefully, I'm guessing. The alpha ketogluteric acid got oxidized, the NAD plus got reduced. The alpha ketogluteric acid was oxidized into succinyl-CoA, the NAD plus was reduced to NADH. And hey, look, we have another decarboxylation reaction happening. So now we've got 4 of our 6 carbons accounted for. We start off with 6 carbons in glucose, we exhaled 2 for the acetyl-CoA step, and now we're exhaling 2 more in this spin of Krebs. Okay, so now we've produced our succinyl-CoA. We have another little kind of weird reaction happening here. I really shouldn't call it weird, but it is kind of weird. From succinyl-CoA to succinic acid, we have a little energy producing step right here, but it's not a direct production of ATP. We have to go through an intermediate GTP first. So hopefully you're comfortable with the idea that GTP is pretty much just like ATP, but is using a guanosine base instead of an adenine base, but it's a triphosphate, nucleotide triphosphate. So that's totally normal. But for whatever reason in Krebs cycle, the GTP is produced and then it just quickly phosphorylates an ADP producing ATP. So we've got 1 ATP produced in this first spin. Okay, so now we've made a little bit of ATP, succinic acid. Hey, look, we have maybe another redox reaction going on here. Let's take a look. Let's write down what we have. So we have succinic acid plus FAD, okay, that's new, goes to fumaric acid plus FAD NADH2. Okay, so again, I'll give you a moment to see if you can predict who's getting oxidized and who's getting reduced. Look for our clues of where the hydrogen, maybe somebody gained a hydrogen. Remember, electrons are going to be traveling along with the hydrogen. So looking and comparing between succinic acid and fumaric acid and FAD and FADH2, we can see the FAD gained H2. So electrons came along with those hydrogens. So that means they had to have come from the succinic acid. So succinic acid was oxidized, FAD was reduced to FADH2. So another redox reaction. Quite a bit of those in the Krebs, isn't there? All right, so that was step 6. Step 7, we just rearrange fumaric acid to malic acid, and we have one last redox. Hopefully at this point, maybe you can already predict what's going to happen. So we have malic acid plus NAD plus goes to oxaloacetic acid plus, excuse me, NADH. All right, so between malic acid and oxaloacetic acid, NAD plus and NADH. Who's getting oxidized and who's getting reduced? So those electrons came in with the hydrogen over here, which means they had to have come from malate, which means malate was oxidized, NAD plus was reduced to NADH. Hopefully you're seeing a pattern by now. So these redox reactions are so critical because what we're doing, because now we've finished one spin, right? So we brought in our acetyl-CoA, it's driving these enzymatic reactions, or enzymes are driving these enzymatic reactions. We've got rid of a couple carbon dioxides, we're producing some NADHs and FADH2, so what's the point? What's the why, right? So we see the things that go in, we see the things that come out, but why do this? Well, the reason is every time we do a redox reaction, we are gaining energy in the form of those electrons, the NADHs, the FADH2s, and all those electrons that are getting stripped away from the carbon molecule that originated as glucose, that catabolic pathway. Remember, catabolism means breaking down. So we break, strip those electrons away from these carbon molecules, temporarily store them in our NAD+, or sorry, NADH and FADH2, and then we're going to utilize those in the last stage of cellular respiration during the electron transport chain, which we are going to get to next. All right, so I will see you then. Bye.